Welcome back to another Explainer. Today, we're taking a journey along the most famous waterway in all of human history. But we aren't just going to look at a static blue line meandering down a map. We're going to completely demystify the Nile River, and we'll be examining it as a highly dynamic, living, breathing hydrological system. From torrential monsoon floods to vast evaporating swamps, the Nile is a geographical marvel just full of surprises. And you know, understanding this river isn't just about geography, it's absolutely crucial for understanding the future of this entire region.
Okay, let's dive right into this by looking at the sheer scale of our subject. The Nile stretches a record-breaking 7,088 kilometers. That's roughly 4,404 miles, from its furthest sources all the way down to the Mediterranean Sea. Because of this incredible length, its drainage basin covers about 10% of the entire African continent, extending across 11 different modern nations, from Rwanda and Tanzania all the way up to Egypt. But here's where we hit the great paradox of the Nile. It's the longest river in the world, right? Yet the actual volume of water it carries is shockingly low. To put that into perspective, the Nile's discharge is only about 1% of the Amazon rivers and just 6% of the Congo rivers. So how can a river system be so incredibly long, flow through massive arid deserts, and yet carry so relatively little water to the ocean?
To solve this mystery, here's our roadmap for today. First, the Great River Paradox. Second, the steady White Nile. Third, the flooding Blue Nile. Fourth, the confluence and cataracts. Fifth, the shrinking delta. And finally, basin sources and sinks.
All right, part 1, the Great River Paradox. To understand why the Nile has such a relatively low volume of water, we actually have to stop thinking of it as a single uniform river and instead break down exactly where it comes from. You see, the Nile's water relies on 3 distinct tributaries, and they are definitely not created equal. 54% of the annual water contribution comes from the Blue Nile, 32% from the White Nile, and the remaining 14% from the Atbara River. The Nile is really a tale of 2 entirely different rivers that just happen to join forces.
Moving on to part 2, the White Nile, our steady source. Let's head down to the very southern edges of the basin to introduce the first character in our story. The White Nile is considered the headwaters of the entire system because it's the longest continuous tributary. It begins way down near Lake Victoria, which is the second largest freshwater lake in the world. Now, the highlands down there experience seasonal rain, but the flow of the White Nile remains remarkably constant year-round. Why is that? Well, it's because the massive lakes and sprawling wetlands of this region act like giant sponges. They soak up the cyclic rainfall and slowly, steadily release it downstream.
If you follow this spatial journey chronologically from south to north, you can see exactly how the White Nile fits into the macrogeography. The water starts in the African Great Lakes region, flows up into South Sudan as the Mountain Nile, formally becomes the White Nile, merges to become the main Nile, and finally fans out into the Nile Delta. But during that second step, the Mountain Nile phase, something really dramatic and honestly a bit baffling happens to the water volume.
Now, what's really interesting about this slide is how the terrain physically alters the river here. In South Sudan, the river hits the Sud Swamp. The incline of the ground is so incredibly flat, just a 1 to 13,000 slope, that the water essentially stalls out into a massive hydrological traffic jam. The river widens out, and lush, invasive vegetation like water hyacinth actively chokes the flow. Because it sits in this massive, hot, flat wetland, the White Nile loses roughly half of its entire water volume purely to evaporation before it even reaches the desert. It's wonderfully absurd when you think about it.
Which brings us to part 3, the Blue Nile and the flood.
Now we shift to our second, much more volatile character. The Blue Nile is an absolute powerhouse. Originating near Lake Tana in the Ethiopian highlands, the Blue Nile's flow varies wildly throughout the year. When the summer monsoon rains hit Ethiopia between July and October, the Blue Nile absolutely surges. During these summer floods, its contribution to the main river skyrockets to roughly 70% of the total water volume. This side-by-side comparison really brilliantly illustrates the dual nature of the river system. You've got the White Nile, sourced from the Great Lakes, bringing light-colored quartz and feldspar in a nice, steady, moderated flow. Then, in stark contrast, you've got the Blue Nile tearing down from Ethiopia, carrying dark basaltic clay, and behaving wildly due to extreme summer monsoons. They are basically geological opposites.
All right, part 4, confluence and cataracts.
So, what exactly happens when an unstoppable force meets a slow, steady object? Well, this climax happens at Khartoum, the capital of Sudan. At this confluence, the visual contrast is stunning.
You can actually see the light grayish waters of the White Nile running right alongside the dark, clay-filled waters of the Blue Nile before they mix. In fact, the Blue Nile's flood is so immense during the summer that the sheer force and volume of its water actually acts like a physical wall, actively backing up the White Nile's flow right at the junction. Once unified as the main Nile, the river carves this massive S shape through the desert towards Egypt. But it's not a smooth ride. Along this stretch, the river crashes through the 6 cataracts of the Nile. These are large, really violent rapids filled with jagged rocks. And this matters because these weren't just bumps in the water. Historically, they made the river utterly impassable by boat. They severely disrupted continuous navigation and trade, effectively serving as formidable natural borders that dictated the shape and reach of ancient empires for thousands of years.
On to Part 5, the shrinking delta. So far, we've seen how nature shapes the river, right? But modern humans have fundamentally altered it as well. To control the wild seasonal flooding of the Blue Nile and to harness its energy, the Aswan High Dam was completed in Egypt in 1970. The facts of this dam are just monumental. It regulates the flood cycle so perfectly that downstream flow is now mostly constant year-round, and it generates a massive 2.1 gigawatts of electricity. However, by holding back all that water in Lake Nasser, the dam also traps massive amounts of that dark, vital upstream sediment we talked about.
So why does that trapped sediment matter? Well, because of this staggering number right here, 150,000 cubic kilometers. That is the historical volume of the Nile Delta, the massive triangular landmass where the river finally meets the Mediterranean Sea. You see, this delta wasn't just there by accident. It was built up layer by layer over millions of years, entirely from the crushed rock and soil carried down from upstream.
So, the crucial point is this: coastlines face constant erosion from ocean currents. Historically, the Nile deposited enough new soil every year to balance out that erosion. But with the dams trapping the sediment upstream, that new soil never arrives. As a direct result of our engineering, the magnificent, fertile Nile Delta is now actively shrinking into the Mediterranean Sea. And this isn't just a geological curiosity. Millions of people literally rely on the agriculture of this shrinking landmass for their daily survival. Finally, Part 6, Basins, Sources, and Sinks.
To truly grasp how precarious this whole system is, we need to step back and look at the entire 2.9 million square kilometer basin purely through the lens of data. Hydrologists categorize regions as either sources that add water to the river or sinks that remove it. Notice the stark divide here. Upstream nations like Ethiopia, Tanzania, and Uganda are massive sources, with Ethiopia adding an astonishing 164 cubic kilometers of net volume. Meanwhile, the downstream nations, Egypt, Sudan, and South Sudan, are massive sinks. They consume and evaporate the water, with South Sudan losing 146 cubic kilometers, largely due to that flat sud swamp we talked about earlier.
This data perfectly illustrates the scientific concept of water balance. Simply put, water entering a region through rain has to be balanced by water leaving through evaporation, soaking into the ground, or flowing out through streams. If the math gives you a positive net stream flow, you have a source. If it's negative, you have a sink. Hydrology matters because understanding this delicate mathematical balance is literally the only way to understand how the entire basin survives.
And you know, it's not just the water we have to think about, it's the physical Earth itself. The 97% rule states that 97% of the transported sediment carried by the entire Nile originates from the Adbara and Blue Nile rivers over in Ethiopia. So Ethiopia isn't just the ultimate source of the majority of the water. It is the literal, physical Earth that traveled thousands of miles to build the lower delta over millions of years. Which brings us to our final thought today. The Nile is an incredibly complex, interconnected system where the actions in the rainy southern highlands directly dictate the survival of the arid northern deserts. As natural sediment shrinks behind modern dams and the populations of all these nations continue to explode, how will the delicate mathematical balance of these sources and sinks shape the future of the 11 nations sharing this singular vital artery? It's a hydrological puzzle that will absolutely define the 21st century for Northeast Africa. Thank you so much for joining me on this explainer, and as always, keep questioning the world around you.